Welcome to another fantastic lesson. This lesson is on transformations of functions. The objectives of the lesson is to transform functions, recognize transformations of functions, and to write the equation of a transformation function. Let's first go back in time and talk about transformations of what's called absolute value functions. We talked about this in semester 1. In fact, if we graph the absolute value function, we'll consider this our parent function, which is the original function we base all transformations from. If we graph the absolute value of x, we notice that it's a V-shaped graph. And a key important point here is the vertex, which lies at the origin here. We discovered in semester 1 that if we graphed the absolute value of x minus 4, where x minus 4 is inside the absolute value symbols, we saw that this shifted the whole entire graph right 4 units. In fact, if we graphed the absolute value of x plus 3, we saw that it actually shifted left 3 units from the original parent function. And we discovered if we graph the absolute value of x plus 6 on the outside of the absolute value symbols, we saw this shifted up 6 units. So if we were to graph the absolute value of x minus 3 outside of the absolute value symbols, we saw it shifted down 3 units. And when we placed a negative in front of the function, we saw that it had a reflection, more specifically across the x-axis. These are our basic transformations of functions that we discovered in semester 1. We also explored it with quadratics, which was our last unit. Now we can represent these transformations of f of x as rules. In fact, our first transformation that we looked at was what's called the horizontal translation. This is shifting the function left or right, but it's opposite of what we think, especially if it's inside the grouping symbols. Since it's x minus h, we actually discovered that it shifts it right by h units. If it was x plus h, it shifted actually left by h units. For example, here we're given x cubed, and I have to describe the transformation of x plus 2 inside the parentheses cubed. Since it's x plus 2 inside the parentheses, it's opposite of what we think. So here it actually shifts left 2 units. The other translation is a vertical translation. This is shifting the graph up or down. What's nice about this translation is whatever k is, whatever sign k is, since k is positive here, it shifted up k units. If k was negative, it actually shifted down k units. And this occurs outside of the function we say. So for example, here's our parent function, the square root of x. Notice how the plus 7 here is outside of the function. It's square root of x plus 7 outside, not inside the square root symbol. Since it's outside and it's plus, it shifts it up 7 units. Another type of transformation that we really haven't discussed, especially in semester 1, is a reflection across the y-axis. Any type of reflection across the y-axis occurs when the negative is inside a grouping symbol. For example, here's the square root of x again, and I ask you to describe the transformation. Notice how the negative symbol here is actually inside the grouping symbol. Our grouping symbol in this case is the square root. So in this case we would say there's a reflection across the y-axis here. The other type of reflection is across the x-axis. This is what we dealt with the most in semester 1 and a little bit of semester 2 with quadratics. This is where the negative symbol is outside of the function, okay, in front of the entire function. So for example, here we're given x to the 4th. Describing the following transformation of negative x to the 4th, this would actually reflect it across the x-axis since the negative is in front. The other two transformations that we talk about is what's called the horizontal stretch and compression. These get a little bit confusing. This is when our some numbers inside the parentheses grouped with x. And it's sort of opposite again what we think. We see a fraction in there, and it usually means that there's a stretch going on. Okay, since b is greater than 1, so if we have b as 2 or 3, you'd see a 1/2 or 1/3 in here. If b is strictly between 0 and 1, okay, our factor of b is like a fraction of some sort, we say that's a horizontal compression. Here's an example. We're given the absolute value of x, and I'd ask you to describe the transformation. Notice how it's 1 over 2 times x, 1/2 times x. Compare that to what our rule is. Well, 1 over b times x, where b in this case, in our example, is 2. Since b is greater than 1 here, okay, our rule says that this is a horizontal stretch. The last and final type of transformation is called a vertical stretch or compression. This is where we have some coefficient outside in front of the function. And this is sort of opposite of what you see with horizontals. If a is bigger than 1, so if we see a 2 in front or a 4 in front or a 10 in front, we say it's a vertical stretch. If we see some type of fraction or decimal be strictly between 0 and 1, a, we say it'd be a vertical compression. So for example, here we're given the cube root of x, describe the following. Notice how we have a 1/4 in front of the entire function, in front of our parent function, so therefore we'd say this is a vertical compression or shrink. Now, these rules actually apply to every function in math. This is called the graphing form of every function. We talked about absolute value functions before. This is the graphing form in an absolute value function, where a, the coefficient of a, well, for one thing, it tells us if there's a reflection across the x-axis. It also tells us if it's a vertical stretch, if you see a number in front. Remember the minus h part. That tells us if it shifts it left or right by how many units. And that plus k tells us if it shifts it up or down. And again, if k is positive, it's up. If k is negative, it's down. In fact, the graphing form for a lot of functions, such as quadratics we just ended one of our units with, has the same form, where a, h, and k all do the same thing. So therefore, any kind of power functions, any power of n, such as degrees of 3, degrees of 4, quartics, quintics, you name it, have the same transformations going on. Square roots, same application. So we could say it's true for all nth roots, any kind of radical function, so cube roots, fourth roots, you name it. It's also true for rational functions, trig functions, and every other function we come across in math. So let's take a look at our first example. We're given f of x equals x squared minus 3. We're going to do two things here. We're going to write the transformation function as an equation, and we're going to describe the transformation. Here's our first transformation. Let's write the transformation of g of x, which is 2 times our function f of x. Well, let's write it out. G of x equals twice our function of f of x. So let's sub in x squared minus 3 in for f of x. And you notice all we have to do to simplify this equation is to distribute the 2 through. And our end result becomes 2x squared minus 6. This is our actual transformation function written as an equation. To describe this, if you notice there's a value of 2 out in front. If you look back on our rules, this means that there's a vertical stretch going on by a factor of 2. Let's take a look at another one. Let's write the transformation of f of x, which is now f of 2x instead of 2 times f of x. This is different. Notice how 2x is inside the parentheses here. When we talked about composition of functions, this is exactly what we're doing in this case. We're going to take our function, we're going to sub in 2x wherever we see an x into our actual parent function of f of x, and we're going to simplify. So notice how our original function was x squared minus 3, and all we did was we subbed 2x in for x. When we simplify, we have to distribute this power of 2 to both of the terms inside the parentheses. So it becomes 2 squared x squared, which when simplified becomes 4x squared. We have the minus 3 still outside. This is our end result equation for this transformation. To describe it, notice how our 2 is inside the parentheses here. There's a horizontal stretch or compression going on. Which one is it? Notice how the value of 2 is inside, which b in this case would be a fraction between 0 and 1. It's kind of hard to think about, but this in case would be a horizontal compression here. Let's take a look at one more transformation of this function. Combination of things going on here. So k of x is going to be negative f of x up plus 5. So in this case, we're taking the opposite of the function. So let's sub in f of x again, which is x squared minus 3 in for f of x. And this plus 5 is going to be outside here. So it's kind of similar to the one above. We want to distribute this negative through first, which becomes negative x squared plus 3. We still have that plus 5 on the outside. Collecting like terms, we get negative x squared plus 8 as our final transformation function. To describe this, notice how our negative symbol is outside the function. This tells us that there's a reflection across the x-axis. And the plus 5 shifted it up by 5 units. So it's a reflection across the x-axis up 5 units as it's describing. So now you try. Here we're given f of x equals 4x plus 1. I want you to just write each transformation as an equation and describe each of the transformations below. So pause the video and try to work these out. We'll go over the answers here in a little bit. Notice how the first one is x plus 2, which is inside the parentheses. This is a good example of a composition of functions. So in our equation of 4x plus 1, we're going to replace x with x plus 2. So it becomes this, 4 times x plus 2, and then the plus 1 on the outside. Again, noticing that we're replacing x with x plus 2. So the only thing here to simplify is really distributing the value of 4 outside the parentheses. So it becomes 4x plus 8. We still have the plus 1. So combining like terms, our end result equation becomes 4x plus 9. Describing this, notice how the x plus 2 is inside the parentheses. So here is a horizontal translation. And in this case, since it's plus 2, it goes left 2 units. Remember, it's opposite inside the parentheses. The next one, we have 3x inside the parentheses. So it's similar to the last one. We're going to replace x with 3x. So what it becomes is 4 times 3x plus 1. The only thing here we have to do is really take 4 times 3x, which is 12x. We still have the plus 1, so here's our end result. Describing this, notice how our 3 is a coefficient inside the parentheses here. So this is in fact a horizontal compression here. The last function has a combination of things. Notice how we're taking negative 5 times our function, then we're adding 3. And that's exactly how we're going to do this. We're going to take negative 5 times our entire function, which is 4x plus 1, and then we're going to add 3 to it. So notice how this is similar to our first one. The only thing we really have to do here is just distribute the negative 5 through. So it becomes negative 20x minus 5, and we still have the plus 3. Combining like terms gives us our end equation of negative 20x minus 2. Describing this is a few things going on. Notice how we have a negative in front, which tells us it's a reflection across the x-axis. The 5 tells us that it's a vertical stretch, and the plus 3 on the outside tells us it's a vertical translation, in fact up 3 units. So as a combination, it'd be a reflection across the x-axis, a vertical stretch, up 3. This concludes our fantastic lesson on transformations of functions. I hope you enjoyed. Try the questions below on the Google form and be ready to practice these tomorrow. Enjoy your night.